AP Chem, guess what? Stoichiometry is back. I personally love stoichiometry. Stoichiometry has to be one of my favorite things in chemistry to do because there's such a nerdy sense of satisfaction when you figure out how much of a chemical you have, how much of a chemical you should make, and then when it actually works out, it's like, whoa, and it's like the greatest thing in the world. So pardon my enthusiasm for stoichiometry, but we are going to be talking about that today and reviewing it from your Gen Chem days. So, if you're a little rusty, we'll dust the old books off and get things caught up for you. So just as a reminder, in case you somehow forgot, stoichiometry is the quantitative relationship among reactants and products. So basically, it's the math that's involved when we talk about how much we have to begin with and how much we expect at the end. And it is, like I said, one of the most beautifully predictive things that we can do in chemistry, and is essentially the fundamental bits of how we do chemical reactions and how we know what we should make when we run a chemical reaction. And it's all based off the idea of the law of conservation of mass. So the idea is that matter cannot be created or destroyed. So if we have so many numbers of atoms before we start a chemical reaction, we have to have the same number after, and they have to be accounted for somewhere. And so stoichiometry lets us kind of predict what we are going to see when you end up with that process happening. And like I said, I just love it because it's just so elegant in the way that it works out. So stoichiometry problems can happen in a number of ways. The easiest ones that we see are mass-to-mass problems, which we're going to kind of talk about today. You can also see stoichiometry problems where you go like mass to moles or moles to mass. You can see molarity in there, and we're going to be touching on those in just like a week or so. And then you're also going to be able to see when you have problems with gases as well. So you see stoichiometry, and thermodynamics. So stoichiometry is like a fundamental piece of chemistry. So it's really, really important that you are good at solving them. And when we talk about stoichiometry problems, the process for solving is always the same, no matter what we're looking at. It's just an issue of picking through the problems and figuring stuff out. So today we're going to be doing a mass-to-mass problem. And I'll show you an example in just a few minutes. But a mass-to-mass problem means that I start with a mass of something and it's asking me to solve for a mass of another thing. But when you start a stoichiometry problem, the first thing you have to make sure that you do is you have to balance your chemical reaction. And I am going off the idea that you guys remember how to balance a chemical equation. So if you need help with that, make sure that you talk to me about that. But the first thing you need to do is you need to have a balanced equation, because the coefficients that are in front of your reactants and products are going to be very important when we talk about stoichiometry. The next thing that's probably the most critical part is that you need to be able to read through the problem and decide what you're starting with and the units that you're starting with, and then what you are solving for. And you need to make sure that you keep track of that. When you solve a stoichiometry problem, you could go from reactant to reactant. You could go from reactant to product to reactant, or product to product. So a stoichiometry problem is just going from one chemical in your reaction to the other. It is not restricted from, like I said, only reactants to products or vice versa. It's just from one chemical to the other. And that's why balancing your equation is super important as well. What you need to do then is you're going to take your starting information that you determined from your problem, and you need to convert that into moles. So when we do that with masses, which we'll do today, you've got to use your molar mass to convert to moles. However, there are going to be situations where we do molarity calculations and you'll need to use a molarity, or you'll have to do it with a gas, like I said, or with an energy term. And you'll be able to do all of those by the time we're done with this. Then what you need to do is you need to use your mole ratio, which comes from the coefficients in your balanced equation. And you're going to use those to switch what chemical you're talking about to the chemical you are going to when you're solving your problem. And then you need to solve for the correct units. And that's why reading your problem is so careful. So I'm just going to go through one example because I'm assuming you know how to do stoichiometry and you just need a little brush up on it. So here is our mass-to-mass problem. And I'll make sure I point out why this is a mass-to-mass problem versus the other types that we see. So here's the background. And one of the things you'll notice in College Board problems is there's a lot of extra verbiage in here. So it says that KO2 is used in a closed system breathing apparatus. It removes carbon dioxide from water and water from exhaled air. The reaction for the removal of water is KO2 plus H2O turns into O2 and KOH, potassium hydroxide. The potassium hydroxide produced is then used to remove carbon dioxide through the following reaction. KOH plus CO2 makes KHCO3. The question they're asking is, what mass of KO2 produces 235 grams of O2? Okay, so when I read through my problem, there is a lot of extra text here. What we need to do is we need to kind of cut through the problem and then figure out what it's asking. So what I'd like you to do is pause the video. I want you to attempt the problem and then we'll see how things go. Okay, so we're going to get into the example. When we look at a chemical reaction in a problem, stoichiometry or not, the first thing you need to do is you need to double check to see if the equation is balanced in here. So I'm going to escape out of here and get to my doc cam so that you guys can see what I'm working on, and then we'll go from there. Okay, so we are going to start off your stoichiometry problem by doing what we said we have to do first always with these, which is balancing an equation. And I gave you a deceptively easy looking equation because you know what? It's not going to hurt us to have to deal with something a little annoying. Okay, so I have potassium oxide plus water turning into oxygen and potassium hydroxide. So when we balance our equations, I always recommend doing everything that's not hydrogen and oxygen first. Then you do hydrogen, and oxygen is last because oxygen always gives us trouble. So what we're going to do is check potassium first. I have potassium and potassium 1 and 1, so we are good to go for that. Hydrogen. I have 2 on my reactant side and I have 1 on my product side here. So to make sure I have 2 of them, I can't just like throw on a subscript of 2 down here. The K and the O come with the hydrogen. So I'm going to put a coefficient of 2 in here. But when I put that coefficient of 2 in, it makes it that I have 2 potassiums. So now I have to fix my potassiums on my reactant side. And so I've got 2 potassiums and 2 hydrogens, and all is right in the world. So then oxygen. Like I said, oxygen is always kind of a pain. So over here, I have a coefficient of 2 and a subscript of 2, which means that I have 4 oxygen. And it might be one of those things that you don't need to do this, but I like to keep track of my oxygens by writing them down because, like I said, they're a problem. And I've got 1 here, which means that on my reactant side entirely, I have 5 oxygens. Over here, I have 2 and 2. So I've got a situation where my oxygens are causing me a little trouble because if I change the coefficient here, then I change the potassium, which causes problems over here, and it just keeps cycling. So I have a problem now with the O. And usually what happens is when I have O's that are causing me difficulty, I look at the O2 and I try to figure out how to make the O2 work for me. And sometimes it ends up that you need a half in your coefficient to solve your problem. So if you think about the oxygen here, if I would be able to put a coefficient of 1.5 in front of the oxygen, I would have 3 O's then, and then I would have 2 on the KOH, and I'd add up to 5, and I'd be balanced. However, when we talk about balancing equations, we want whole numbers in front. So to fix that, what I'm going to do is I'm going to multiply every coefficient by 2. So 2 becomes 4. This 1 that's implied here in front of the water becomes a 2. The 1.5 becomes a 3. And the 2 becomes a 4. So like I said, this is kind of a gnarly equation if you aren't careful with it. And oxygens always cause the problems. So the problem, I'm going to rewrite this just because it's kind of messy. Oftentimes, if you do this, it's easy to miss a coefficient. So I like to rewrite it, assuming you have enough time to do that. So the next step that I suggest is taking your problem and reading through it and then identifying where you're starting and where you're going to. So it said that I want to produce 235 grams of oxygen and I need to know how much KO2 it took to make that happen. So what I like to do is I like to read through my word problem and write down what I have. So I have 235 grams of oxygen and it's asking me how much KO2 I need. So my problem is going to be going from a product to a reactant. And then I like to write a question mark and then the unit here so that I remember what I'm solving for, because sometimes it's easy to get lost in your problems. And if you mentally do this, that's totally fine. But if if I'm teaching it, I might as well go through the whole process. So with that, we are going to solve. I'm going to start with my 235 grams of oxygen. Now, unlike empirical formula, it's talking about O2 in this situation. So we have to deal with O2 in our molar mass. So I've got 235 grams of O2, and always with stoichiometry, you're going to take this starting number and you're going to turn it into moles. If it was in moles already, you could skip to the next step, but it's not. So we are going to do a little bit of dimensional analysis. If we look at our periodic table, 1 mole of O2 weighs 32 grams. And so when I do this step, what I have effectively done is taken my 235 grams and converted it to moles of oxygen. So if I were to stop here and hit the equal sign on my calculator, I would get moles of oxygen. Now my problem is asking me to solve for grams of KO2. And what we need to do is we need to take a look at how many moles of the oxygen it is produced when I have so many moles of potassium oxide. And that ratio comes from these coefficients in front. So if I have 4 moles, or, in theory, 4 molecules of KO2 that react with an unlimited amount of water, I would be able to have 3 moles or molecules of O2 show up. So our mole ratio comes from these coefficients in front. It talks about individual particles of the substance, but that scales up, and we can also talk about moles. So the mole ratio then is going to be 3 moles of O2 on the bottom to cancel units out with my dimensional analysis. And then 4 moles of KO2 on the top. If we think about units, grams of O2 and grams of O2 cancel each other out like a fraction. Moles of O2 and moles of O2 cancel out. Now, if our problem were asking us to solve for just moles of KO2, we would be done because our units are in moles of KO2. However, it's asking us to solve for grams of KO2. And this is where we call it a mass to mass, because I'm going from one mass of one chemical to a mass of the other chemical. That means that I am going to have to solve for grams of KO2, but my answer currently would be in moles of KO2. So I need to do some converting, and that's where I'm going to put 1 mole of KO2 on the bottom. And that's because I want to just convert using the molar mass. Now, the molar mass of KO2, calculated by my periodic table, is 71.0 grams for 1 mole of KO2. And then I'm going to put this whole thing into my calculator. My moles of KO2 cancel out. I'm going to put this into my calculator, and I am going to scooch this up here a little bit so that you can see how I put this in. Now, when I put these in, you could do the whole top multiplication and then divide by the bottom, but I see lots of people make errors on this when we put it in. So my personal preference is to ignore any ones in here, but then I go like basically fraction by fraction and then put it into my calculator. So I am going to do 235 grams of oxygen. I'm going to ignore this one here. I'm going to divide by 32. I'm going to go back up to the top, kind of like a zigzag. I'm going to multiply by 4, down, dividing by 3, back up, multiplying by 71.1. And my answer that I get here is 696.19 grams of KO2. And since I started off with 235 here, then I would have 696 grams, of KO2. If I would have put 235.0, then I'd have 696, why do I keep writing that wrong? 0.2 grams of KO2. Okay, I want to show you what happens when you do this incorrectly, because I see this happen a lot with students. So they will multiply all the top here. They'll do 235 times 4 times 71.1, and then they'll hit the divide key. They're like, oh, I've got this. I'm going to go divided by 32 times 3, right? And you get a number that's 6,265. And the reason why you get that is because if you think about order of operations, right here I hit the divide sign, then I do divided by 32, and even though my brain says I need to divide also by 3, my calculator is getting the message that I'm going to multiply by 3. So you could do the whole top divided by the whole bottom, but you need to make sure if you're going to do that you have parentheses around the whole bottom so that your calculator understands the command that you think that you're telling it. Because if I do that, I get 696.18 then. Okay, so stoichiometry, back with a vengeance. If you have any questions, please make sure that you ask me during a meet. Otherwise, good luck.